In this video, I will give you an introduction to Faraday's law. I'm going to start with the two cases that we have seen before. This is a bar magnet and this is another bar magnet. I have a loop. This is made from a conducting material, and the same thing here. Now, I don't show any current meters, any ammeters, or any light bulbs in this loop and in this loop, but I will keep in mind that you can do this experiment by attaching a bulb in those two circular loops. Now, the two cases that we have seen, the first case is where you keep the bar magnet stationary and you move the loop. And you have two options. Well, you have an infinite number of options really, but let's say we can either move the loop towards the bar magnet or away from the bar magnet. Now I'm choosing to move it towards the bar magnet. And in the second case, instead of moving the loop, I keep the loop stationary and I move the bar magnet towards the loop. Now, in the first case, the bar magnet, of course, will produce a magnetic field at the location of the loop. And because this is made from conducting material, of course, I know that I will have those mobile electrons, the electrons that essentially create the entire mobile charge C inside the conducting material. Okay, every atom donates, if you want, an electron. Typically, in most cases, it's an electron to that mobile electron C, and those mobile charges are free to move everywhere in the conducting object. Now, okay, I'm going to illustrate. I'm going to show just one. Now, because we move the loop towards the magnet, as a result of moving the entire object, of course, the electrons, these mobile electrons, also have the same velocity. If you're pulling the loop, you're also pulling the electrons that are present in the loop. What this means is that for every mobile electron has a velocity because you're pulling them. Now, because the bar magnet creates a magnetic field everywhere around it, at the location of the mobile charge, the moving mobile charge, there will be a magnetic field. So at that location, there will be a B. Now, I don't really care about the direction of B at this point. It depends on whether this is the South Pole, the North Pole, and at what point exactly you're considering the charge to be. I don't really care about the direction. The important thing here is to understand that this moving electron, this moving mobile electron, is inside, it's in the presence of an external magnetic field. We know that to have a magnetic force, we need to have a charge, we need to have a magnetic field, and the charge needs to be moving. It needs to have a non-zero velocity inside that magnetic field. This is what I have now. I have a charge that is moving and it is in the presence of an external magnetic field, the one created by the bar magnet. This magnetic force, this is the cause. Okay, because there is a magnetic force on those mobile electrons, this is going to start moving around the loop, and this is going to create your induced current in the loop. If you have a light bulb here attached in the wire, then you will see that the bulb has light. This is because the mobile charges are flowing in the wire. This magnetic force, this is the cause of the induced current. I want to make it clear this phenomenon is not Faraday's law. Okay, not Faraday's law. This phenomenon is that you get an induced current, an induced EMF, because you have charges moving inside a magnetic field, magnetic forces. The other one, okay, since I mentioned, I guess, that this is not Faraday's law, I guess you can make the assumption that the next one is Faraday's law, and you are right. This is Faraday's law. Now in this case, I have the bar magnet, and the bar magnet is moving towards the loop. Again, I have a mobile charge shown here. Now, at the location of the mobile charge, I will have a magnetic field as I did before, because the bar magnet creates the magnetic field here. There will be a B. Now, this mobile charge though is not going anywhere because I'm not pulling the loop. The velocity of this mobile electron is 0. If the charge is not moving, of course we know magnetic forces depend on that velocity. If your velocity is 0, this means that the entire magnetic force is 0. Magnetic forces cannot cause the induced current. Okay, they cannot. Now I want you to think about what happens if you are in the location of that mobile electron. If we consider that we are at that location of the mobile electron, because the bar magnet is moving closer and closer to the wire loop, the distance from the mobile electron to the bar magnet decreases as time goes by. Because the bar magnet gets closer and closer to that mobile electron, the magnetic field will get stronger as time goes by. Now, I don't want to focus on the fact that the magnetic field is getting stronger. The important thing here is to understand that the magnetic field at the location of the mobile electron is a function of time. Whether it's increasing or decreasing, it doesn't really matter. The important thing is that the magnetic field changes as a function of time, the magnetic field at the location of the mobile electron. Now, when we have a magnetic field that changes as a function of time, this is always accompanied by an electric field. Now, I will make it more specific. It's not the kind of electric field we saw at the beginning of the semester, where the electric field was created due to charges. I don't see any charges around here. There is no charge distribution. I don't have any charges to create an electric field. This is why we call this the non-Coulomb NC, a non-Coulomb electric field, because it's not created by charges. Now, and I want to spend a minute talking about the word accompanied. Anytime that you see you have a magnetic field that changes as a function of time, it comes with a non-Coulomb electric field. When you have one, you have the other one. Okay. Now, and this, okay, where I want to go, this non-Coulomb electric field, we know, okay, if there is an electric field at the location of the mobile electron, of course there will be an electric force. And that electric force is pushing that mobile electron, and that's how we get in this case, the induced current. In this case, the induced current is not due to magnetic forces, because we saw there cannot be any on those not moving mobile electrons. But this induced current is now due to an electric field. and in particular to a non-Coulomb electric field that we have because we have a changing magnetic field. This is Faraday's law. Okay, when you have the non-Coulomb electric field creating your the induced current in your system, this is what we call Faraday's law. And to give you a mathematical expression for this, Faraday's law is the induced EMF, let's say EMF induced, is equal to minus the change in the magnetic flux over delta T. Now, of course, if we're dealing with infinitely small time intervals, this becomes a derivative minus d phi, the magnetic flux over T, over dt. And this, the negative rate of change of magnetic flux will give you the induced EMF. This is Faraday's law. Okay, the physical origin of the induced current here is the non-Coulomb electric field, and you can calculate, you can find the induced EMF by finding the minus the rate of change of the magnetic flux as a function of time.